Hey guys, we're Lone Star Power, Group 25, and our team consists of myself, Kevin Glavis, the quality engineer, Danny Larson, the project manager, Christian Fifi, our project software engineer, and Elias Rubalcaba, our project engineer. So our project idea is an autonomous robotic solar tracking system that can easily be controlled remotely through a user interface application and can be installed on any computer, phone, or can be a wall-mounted device. Our project sponsor is CPS Energy, and we're collaborating with two other teams, the mechanical engineers who built the solar tracking moving parts, and the other team is working on the solar tracking software. Our main objective is to develop a friendly user interface that can display power output for the day, total usage, store historical data, and monitor any sensor and notify the user of complications within the system like low pressure on the actuators or any malfunctions. I will now pass it on to Elias, our project engineer.
The solar panel array will be mounted on a metal frame on the facades of buildings and structures. A microcontroller on the panel will automatically determine the optimal orientation of the panels for maximum power collection. It will then control the pneumatic solenoids using inputs to pressurize soft actuators, altering the solar panel's orientation throughout the day. There will be safety measures incorporated in the software for high winds and leaking actuators as well as recalibration. Here is a hardware diagram that shows the layout of all the hardware that's being utilized in this system. Here we have actual images of the components of the hardware that are being used, such as the buck converter, the pressure regulator, the relays, the Raspberry Pi, the Arduino, and the inclinometer.
Here you can see the array of panels, and I can show you up close what all of the teams are testing. CPS is interested in these soft actuators. They are inflatable cylinders molded from rubber that provide linear motion as they are pressurized. Each panel has three, allowing the panels to track the sun effectively on two axes. The advantage of the soft actuators is the fact that each panel need not move independently from the others. They always point in the same direction, so the actuators can all be inflated using the same pneumatic tubes. So there's three lines of compressed air that run to all of the panels, and the microcontroller interacts with the pressure regulators that angle the panel in the direction that it needs to face. However, in order to monitor and collect data on the power generation of the solar panels and utilize its functions such as tracking the sun, calibrating the inclination and pressures, or disabling the panel in the event of bad weather, the project needs a software system that allows for long-term storage and accessibility of sensor data, as well as remote control of the operation of the panel through a cross-platform graphical user interface. This is the main focus of our team's project. We chose a server-client software architecture pattern for our system design called the three-tiered approach, which will give us a robust system that scales well with data and gives us flexibility in the API that we provide the other teams when integrating our code. Specifically, the data is logged through a RESTful interface, which insulates the other teams from any potential changes in the way that we store or access our data. The system has three components that handle data storage, networking and hardware system integration, and front-end interface. We use an SQL database, PostgreSQL, for efficiently storing and accessing large amounts of data. Network communication with the panel is facilitated by an HTTP server running the Python Flask framework that handles requests for the data and controls. The GUI uses Google's Flutter, a framework that provides pleasing material design interfaces on both desktop and mobile, written in Google's new Dart language. The Flutter framework provides UI hardware abstraction, making the UI available as both a mobile and desktop app, and also provides a responsive, aesthetic look and feel. The UI has a live data feed with a power generation graph, including historical data for any time period at the day, week, and month level scopes. Monthly power generation is given as a daily average, while the weekly and daily power values are shown using all of the power data points, just as they are collected. For this demonstration, we filled the database with replicated data that peaks roughly around noon, like the actual solar data. except there is little variation in the value seen here. You can see that the user is able to navigate between time periods using the arrows and buttons above the chart. The UI also fetches a live list of available controls from the server, displayed as buttons that remotely call procedures on the Raspberry Pi.
Thank you. On our next slide, we have our poster. And here you can see that some improvements we want to work on is to implement machine learning to predict power output based off of historical data, send push notifications to the user, schedule custom tracking methods, and implement Bluetooth as well.